Hello my dear students, today's video is about Gauss Divergence Theorem. It's a very important theorem regarding your examination point of view related to engineering mathematics and also physics. So this video explains the theorem, the concept and also an application in form of a question. So look at the video to get more information. So hey students, welcome to another video. And we are starting Gauss Divergence Theorem part 8 from vector calculus. So if you haven't visited part 1 to 7, I will first of all tell you to visit those parts before you reach this part. And I am already giving this details of all the part from part 1 to 7 in my I button. And at the same time, I will be giving in the description below on my particular video, on this particular video in the descriptions. So now let us start Gauss Divergence Theorem from vector calculus. So first of all, let us come with the concept of Gauss Divergence Theorem. What exactly is Gauss Divergence Theorem? So if f is a vector point function having continuous partial derivative in the region bounded by closed surface S, then triple integral v nebula dot f dv equals to double integral f dot n cap ds. Now, if you have gone through the surface integral and the volume integral, which I have mentioned in my previous parts in vector calculus, this is a combination of these two integrals put together. So by the help of Gauss Divergence Theorem, we can change a surface integral into a volume integral and a volume integral back into a surface integral. That is the first advantage of this theory. Secondly, as you can see over here, this is nebula dot f, which stands for divergence of the vector f. And when you are putting a triple integral v, which is the volume integral, you are getting double integral s f vector dot n cap ds, which is none other than flux. So the divergence, the volume integral of the divergence is giving you the flux. This is the basic idea of the Gauss Divergence Theorem. Now, there is a Cartesian form also attached with the Gauss Divergence Theorem, which helps you to convert the same thing, that is the triple integral, into a double integral, but this time in the Cartesian coordinate system. So this goes like this: triple integral v del f1 del x plus del f2 del y plus del f3 del z, that will be equals to double integral f1 dy dz plus f2 dz dx plus f3 dx dy. Pretty similar to the last theorem which we discussed, that is the Green's theorem. It is simply the Cartesian form, or you can say the normal form of any particular theorem. Here, in case this is the Gauss Divergence Theorem. Now let us go with a question, and from this question we can get the idea how we can implement this particular theorem in our answers. So here you have a question where you are given an equation, that is double integral s x cube dy dz plus x square y dz dx plus x square z dx dy. Now if you look at this particular equation, doesn't it sound similar to this particular equation, right? So this is f1 dy dz, f2 dz dx plus f3 dx dy, and something similar to that, x3 dy dz plus x square y dz dx plus x square z dx dy. That is the first clue that they have given the same pattern as that of the double integral in the Cartesian form, where S is the closed surface consisting of circular cylinder x square plus y square equals a square. So this is the equation of a circular cylinder. As you can see over here, this is the particular cylinder, okay, and here the region, that is the boundaries that are given, are z equals to 0 and z equals to b. That is, if this place is z equals to 0, as you can see, since this is on the origin and this is on the xy plane, so here z will be equals to 0, and here somewhere z has a value of b. So this is the cylinder, the circular cylinder that has been drawn, and the equation of the cylinder is given as x square plus y square equals a square, and this is the region where we are going to put our integral and we have to evaluate this particular thing. That is the question. Now the question looks a little complicated, to be honest, but after you apply the theorem, you will be seeing that it's very easy in order to go through this particular answer. In just a flash, you will be able to answer this particular question. Let us see how we are going to do that. So the first step that we are going to do is converting the surface to vector integral form. So as you have seen, this is the Cartesian form, which I have again written over here. So the Cartesian form is the triple integral v del f1 del x plus del f2 del y plus del f3 del z dx dy dz, and that is equals to the double integral form of f1 dy dz plus f2 dz dx plus f3 dx dy. Now if you watch carefully, as I've already mentioned, that this particular equation is exactly the same as the pattern of this one. So if I actually relate this particular equation with this particular equation, then I can get the idea what can be the values of my f1, f2 and f3. We just have to exclude this dy, dz, dz, dx and dx, dy. So like this, we have concluded that the values of f1, f2 and f3 are this one: x cube for f1, x square y for f2 and x square z for f3. So these are the three values which we have picked. Now in order to convert them into a vector integral, it should be volume integral, not vector integral, sorry, it should be volume integral. So in order to convert it into the volume integral, what we need to do is simply we need to put this f1 here, we need to put this f2 here, we need to put this f3 here. So basically what we are doing del x of this x cube, del y of this x square y and del z of this x square z. So this is our next step. So here as you can see, this is del f1 del x del f2 del y del f3 del z, because we are now directly converting the second integral, I mean the surface integral, into the volume integral, into the triple integral. So this is del x of x cube. So del x of x cube is obviously 3x square. Del x of x square y, again y should be here of the use, and the x square will be here as a constant. So x square put aside, del x of y is 1, so x square is remaining, and similarly here x square is again put aside and del z of z will be 1, so x square again remaining. So ultimately the result that comes is 5x square. This is the result of this particular integration. Now we can directly get the volume integral form of this particular double integration that was given to us. So this is part 1 or step 1 of this particular process. Now step 2, as we have done for the other parts, the same thing, that is to find the path of integration and put the limits. Before that, you can't even imagine of going into the particular volume integral because you don't know the limits, so you can't be able to move any particular step ahead in this process. So what can be the path of integration for that? Here there is a little bit of thing that we need to do. As you can see here, we have two diagrams. The first diagram represents the cylinder, and the second diagram is just the particular circular region which has been again drawn here. So if you focus on this, the circular region has a radius of r, which is equals to a. Here we have considered, because here according to the equation r is equals to a, and here the regions are 0 to b, that has already been mentioned. So what we are going to do here, we have to convert the Cartesian form into the polar form. This is the step which we have to do here. Otherwise we won't be able to do this particular problem. So this is a little bit of an extra edge that we have to consider over here. Because of the restrictions of the questions, we have to understand that we can't perform using this particular differentials operators. So we have to convert it into a polar form. So now we are converting x into r cos theta, as we know how to convert a Cartesian into a polar form. We have read it in class 12th. So we are converting x into r cos theta, we are converting y into r sin theta, and automatically z will be z, because here z has nothing to do with the polar form. Here we are only concentrating on x and y, and as a result of putting these values, if you put these values in the equation of the cylinder, as you can see here, the equation of the cylinder is mentioned over here. So if you are putting x equals to r cos theta, so it should be r square cos square theta, and y square equals to r sin theta, so it should be r square sin square theta. So this cos square theta plus sin square theta turns out to be 1, and finally we are left with r square equals a square. So it reduces to r equals a, and yes, dx dy dz will be transformed into r dr d theta dz. Now there is a story behind that. Now there is a transformation theory which states why dx dy dz will be transformed to r dr d theta dz. So here if I explain it, it will take a lot of time. So if you want me to make a video, or if possible I will make a video later on regarding this particular change from dx dy dz into r dr d theta theta dz. This is something related to the Jacobian form of your application, the Jacobian forms where in engineering mathematics that we apply. So using this particular form only we can be able to change this dx dy dz into r dr d theta dz. So for now we are considering that we can directly change this dx dy dz into r dr d theta dz. Now again, along the radius OA, r varies from 0 to a, which has been clearly mentioned in the diagram. So if you are talking about the radius, so the variation of r, here r is 0 and the top of the periphery of the circle r is equals a. So this is the variation range of r. And as for theta is concerned, so theta will be something from 0 to 2 pi. It is pretty much clear because 0 degree means the start of the circle and 2 pi means the completion of a particular circle. And along the volume, we have already mentioned z varies from 0 to b. So these are the three different parameters, the different limits of your r, theta and z. There are three different limits now. Previously there was dx, dy, dz. Now there is dr, d theta and dz. So these are the three variations that we have used and these are the three limits. So this is step number 2, to put the path of integration and to put the limit of the particular integrals. The next step is the final step, that is the application of the integration. So now what we are going to do, we are going to integrate a triple integral and we have got three different parameters. First is the z, which ranges from 0 to b. Next comes theta, which ranges from 0 to 2 pi. Next comes r, which ranges from 0 to a. Now as you can see, the answer that we got was 5x squared dx dy dz. Now x will be equals to r cos theta, so x square should be r square cos square theta. So it should be 5 r square cos square theta and this will be a combination of r dr d theta dz. So if you put all of these values over here, we can put aside 5 because that is a normal number, so that has to be put aside anyway, that is not functioning in this particular matter. And r square cos square theta, that stands for this x square, and the rest of the thing is dx dy dz, that is r dr d theta dz. Now this r and this r square, this r and this r square can be r cube, that's for sure, and this cos square theta remains as cos square theta, and we are getting the different operators over here. Now one step which I have skipped over here, that is I have done all the integrals together. Not mandatory, not necessary. If you are not confident enough, you do one by one. You first of all go with the theta or whatever you feel like going. You can go with the dz operator first, followed by theta, followed by r, or any of the things. Just go according to your wish, but make sure that your answer is correct. So I have done all of this together because you can see here there is no other operations for z, so I can directly operate z here. So I've done it. And I'm getting the limit from 0 to b. Again, I have done for operations of r square into r, which is r cube, and when you operate it, you integrate it, and you are getting r4 to the power 4 by 4, and the limits are for r, that is 0 to a. And finally, we are left over with the limit of 0 to 2 pi 1 plus cos 2 theta by 2. Now we have reduced this cos square theta thing into 1 plus cos 2 theta by 2 again. It is a trigonometrical identity, class 12 chapter. If you are not comfortable with that, please go and see this particular chapter, and anyways I'll be putting videos on that also after this particular vector calculus and all things are settled. So I'm trying to put one video every day so that I can speed up the process, so please bear with that. And if you want information much before that, or if you want it ASAP, so I will just tell you to go through the chapter once, you will get the that particular formula here. So this is 1 plus cos 2 theta by 2. That is the combination for this cos square theta, and now we are going to integrate it. So first of all, we are going to take half aside, because in both the cases we are getting half after the integration. So whatever is left is theta plus sine 2 theta by 2, and we are going to integrate over the limits. We are going to put it over the limit 0 to 2 pi. So after putting the limits, the leftover that we are left with, this is something 2 pi here. If you put 2 pi here, so you are getting this particular answer after you are putting this. I'm not going too much into the details because I have explained step by step. It's not necessary. It's just an integration. You just need to put the values and you will see you are getting the same result. Okay. So this is the final answer that we are getting. 5 by 4 pi a to the power 4 b. So that is the final answer of this particular integration thing, and that is the answer of your Gauss divergence function. So how we have done it? First of all, what we did, we converted the surface integral into the volume integral, then we put the limits, and finally we expanded this volume integral. So these are the three steps we need to do. And yes, again I'm mentioning every time, in every video I mention the same thing. The path of integration is the most important function. If you don't make it correctly, you won't be able to do this particular question. So please make sure your path of integration is absolutely perfect before you are entering into the integration scene. Okay, and I've told you over the videos how to go through this part of integration and things. So if you are not confident enough, please watch the videos over so that you can get the ease of going through this path of integration. So with this, we are wrapping up today's video that was on Gauss Divergence Theorem. So I hope you have got the idea how we are going through this Gauss Divergence Theorem. Very easy thing. Just need to remember the formula, remember the transfer, how we have done this particular transformation from surface integral to volume integral. That is the only thing. Otherwise, everything is very, very easy. Just you have to put the limits, you have to put the integration thing. It's pretty much easy for you guys. So I hope it's pretty much understood to you guys. So in the next video we are going to meet with another theorem, very important theorem, vector calculus, and we'll be wrapping up. After that we'll go with some other theory that comes later on. But anyways, thanks for watching this video, and I'll see you again on the next video. Bye bye.